So let's return to the question of counting, balancing Lego towers using the new toolbox that we have from the inversion chapter. So let me remind you that we're interested in counting the number of towers made with Lego that are balancing. Actually, we're looking at the ones that are maximally balanced in the sense that the center of gravity is straight on top of the center of the base brick. We found a nice way of computing this using a remember table of a recursive program, and we could very easily compute hundreds of entries like this. And in the book, there's a fairly long discussion about how you can tweak this program and create the optimal setup for creating as many observations as possible. So for what I'm going to do now, I'll make do with fewer entries because I have a slightly different agenda here. But in the book, there's a big discussion about how to squeeze as many data points out of this sequence as you can. But for now, let me just naively compute the first number of terms. This is roughly, I mean, this is just one or two fewer than what Watson had in the original paper, and let me just go straight to OEIS and look it up. As you can see, I get a hit. The description of the hit is somewhat different from what we're looking at. It's the number of solutions to a certain equation, where the solutions and the variables have to take values in plus minus 1 or 0, and where these weights, there's some weights on top of the variables. It's 1 times k1, 2 times k2, and so on. Now, there's also an explicit reference to the Lego Towers paper by Watson, and in fact, it's also mentioned here that, I mean, this is a fairly old paper, and that paper made it into the Encyclopedia of Integer Sequences, excuse me, when this was in a book, and so this is something that has been stored in the in Sloan's data for a very long time. But there's a couple of things we need to think about now. First of all, are we sure that this is the same? The number of solutions here is the same as the number of Lego towers. Well, yes, the point is that actually what happened to me was I was looking up this sequence, being interested in these kinds of problems in the online encyclopedia some years ago, and then I found two entries with the same values. The one entry was related to the online to the Watson paper, that's this one here, and the other one had the description given up here. And so since it was the same data, of course, it was natural to think about whether or not this was the same. And I could convince myself that yes, it was indeed the same. I'll give you the argument in a second. Then I wrote to the OEIS people saying these two entries that are have the same values, they are mathematically the same, and I explained why. And then they sort of merged the two sequences, and now it has the form that it has now. I think this is a very typical way of how the OEIS works. There's a bunch of data that people put in. Sometimes people will notice various cross-references and so on, but very often this is noticed by other people who sort of come by looking for one thing and finding another. And then when you can see it's the same, then, I mean, the data looks as though it might be the same, then you can try to see if you can prove that it's the same. And then if that is indeed possible, this will, if in some form, go into the OEIS like it did here. And why is it the same? Well, the thing you should think about is that suppose I have this tower now of Lego bricks, and I want to count the ones only that have the maximal stability. Essentially, what happens is that when you think of you fix the base brick, and then you think of the next brick, and you think of moving that, because there's three choices. Either you put it straight on top, once to the left, or once to the right. And what are those choices? Well, the thing that you're moving is that you're not moving only the base brick, you're also moving all the bricks on top. So the weight of the building that you're moving is n. if we assume that there's n plus 1 bricks to begin with and we fix the base one. Right, so relative to the base one, when I'm moving the lower one, I'm shifting a weight of n. Then when I have the next choice with the next at the next level, I'm shifting a weight of n minus 1, and so on until I'm at the very end, where I'm just shifting the brick at the very top. So this is fairly clearly the same. The number of solutions is exactly the number of choices where you go left, straight on top, or right, in a way such that the center of gravity is exactly on top of the base brick. So this is why this is the same. What is interesting here is now that we have this also gives us a new way of computing these numbers. And there's an explanation here, a formula. It's a coefficient of some specific power of x in a product of some polynomials of the form 1 plus x to the k plus x to the 2k. Or maybe a little bit easier to understand, it's the coefficient of 1 in the product of 1 over x to the k plus 1 plus x to the k. I'll explain this in a separate discussion, but the point is that we're doing something very similar to when we're working with generating functions. This x doesn't really make sense. It's not a variable that we need to work with, but it is a kind of a placeholder for keeping track of the data that goes into these weights. So let's not think more about that right now, but this is something that can fairly easily be understood. What's interesting here is that also there are some programs, and I want to use those programs and see if I can compute the numbers more efficiently this way. There's a Mathematica program that doesn't really make so much sense to me, but there's a Maxima program that looks promising. I think it looks promising because it looks quite a lot like Maple. On the other hand, I don't know Maxima, so my idea is to just take this program and plug it into Maple and see what happens. So I take this program that was given to me by the online encyclopedia, and knowing that it's not Maple, I type it in anyway, and Maple helps me saying, okay, product doesn't come with 4 arguments in a Maple code. It comes with 2 arguments where you, instead of saying k, 1, and n, you will have to say k goes from 1 to n. And then this looks like now Maple understood it. It's the coefficient of this value here of x in this product. However, when I do it this way, you see this is not going to work. That's because this is a strange mixture of an expression and a function. So I need to go like this, like we do in Maple. And now you can see that we're getting something that is very promising. The only thing is that it's shifted once as related to the original sequence. And it's very important for me to stay with this convention that I've chosen already. So I will replace n by n minus 1. So it should come like this. And now I have the exact same sequence. And now I'm going to ask Maple to compute some terms. I'm going for 200 terms because that is something that we have time to wait for. And now from in the remaining discussion, I'm going to stick with these 200 terms. Right, so notice that this is data that I'm using the program that I found in the online encyclopedia, but of course I could have used my own program as well. Later we will discuss which of these methods is better. So I'm not entirely done with the discussion of efficiency of computing these numbers, but for what I want to do right now, it's not so important. Because the thing that I would like to do now is to see if I can come up with a candidate of the constant which relates these numbers to 3 to the minus 1, 3 to the minus n times n over 3 halves. So remember that we found by looking at this data that it was tending to grow as an expression like this. So my program has show you this one here. So this expression here, or rather 1 over this expression, seemed to be a good expression, a good description of how this would grow. So I'm going to compute these numbers. Okay, this is not so readable. Right, so when we did this the first time, we said it looks like the growth of these numbers is like 3 to the I minus 1 over I times the square root of I. So this was our candidate based on observations for the proportional description of this growth. So what we were conjecturing was that these numbers grow like some constant times this number here. And I want to see if I can guess the constant with the help of identify and other inversion tools. So I will simply ask Mabel to compute the fraction between the correct observations and our guess and see what numbers we get out. Right, so I'm going to use because I intend to use identify, I'm going to use a high level of precision. And you can see that it's not a problem to compute these numbers, and indeed they also seem to converge in a nice systematic way to this number, which is somewhere around 0.84. However, if I ask to identify, this is not going to work, and even if I multi-identify, which is often a good idea because we will sort of look at various levels of precision in this computation, then I'm not going to get anything useful, which you'll see in a second. So here we get the hits. You can see I get various things out that look sort of interesting, but looking closer at these are not, in the beginning, they're not very good approximations, and in the end, they just get weird. So I don't think there's anything here that we can use. But the idea that I have now is to try to use the methods of approximation that we know from other areas of math to see if we can actually guess a better approximation of this constant than what we get by going to the 200th term. And this is the purpose of the next video.